In today's video, we're going to look at finding limits algebraically. And these techniques that we're going to learn today is to help us solve any limit problem without having to go to the graph as we learned in our last section. Now, this first problem, we're going to solve it, we're going to use the direct substitution method. But before I solve it via direct substitution, I want to show you that this does have the properties of limits that we learned in last class. You can solve it with the properties of limits, but direct substitution is like a shortcut to the properties of limits that we learned last class. So I'm just going to solve this with properties. So I have multiple terms here. So the property says I can distribute that limit to each term. And then I can have a multiplying by constant, so the constant comes out. Constant comes out in this middle term. And this is the limit of a constant. So we have a property for that. And I recall that if I have x raised to a power, that is equal to the c value, which in this case is 1 raised to the power. And then the limit as x goes to, oh, I should write another 4 there. That should be just x. I took the 4 out. The limit as x goes to 1 of x is just 1. And the limit of a constant is that constant. And so that gives us 3 plus 4 minus 5. Well, that took a lot of space to get to our answer here as we work through this. And so we want to find a better way of doing this where we don't have to do that much space as we work through it. So what we're going to do is our better method of solving this is called the method of direct substitution. And it's just a shortcut to this properties method I did over here on the right-hand side. Now, direct substitution method says in order to evaluate a limit at a given x value, all you do is substitute in that value in place of every x in the original function. So you notice that this gives us right to this step here. So it lets us skip a few steps. And then once we do that, we just simplify down. So it gives us 3 plus 4 minus 5. That's 7 minus 5, which is 2. So our answer is 2. So direct substitution is you directly substitute every x value with 1 and then simplify down. Now this step here where I directly replace every x with 1, I must do that step. Now the next step when I have that 3 plus 4 minus 5, you can write that or you can just punch it straight in your calculator or do that math in your head and go straight to 2. But I just need this step here and this final answer, or the steps I need to see for direct substitution. So that is our default method of solving limits algebraically. Every limit algebraic problem will start and end with direct substitution. You'll start with direct substitution. If you run into a problem using direct substitution, you'll use the techniques that we're learning the rest of this section, and then at the end, go back to direct substitution. So begin and end with direct substitution. Now, if this worked in every problem, life would be wonderful. But unfortunately, not every problem can be solved using direct substitution. One of the most common problems that cannot be solved using direct substitution is any equation that when you do direct substitution, you end up with an answer that's in the indeterminate form. Now, what is the indeterminate form? Okay. So there are many indeterminate forms. There's actually 7 of them that you'll use in calculus. There's a couple more, but the 7 are the most common that you'll see. For this section, the one that you'll see most often is 0 over 0. Later on in this semester, we might see some of the other ones, so you need to be familiar with those. And you'll definitely see it in Calculus 2 and Calculus 3 if you go on, see any upper level calculus. So the most common indeterminate form is 0 divided by 0. So that is does not exist because, I mean, you've always learned you cannot divide by 0, but you're taking 0 divided by 0. And you also learn that any number over itself is equal to 1. So is this undefined or is this 1? We don't know. It doesn't match all the rules. So that tells us we have to do some other technique in order to evaluate this limit when it's in the undetermined form. Now, the 7 undeterminate forms you need to learn for this calculus course is, of course, 0 over 0. Infinity over infinity. Now this can be plus infinity over negative infinity or plus or minus. Negative infinity over negative infinity. The sign doesn't matter. Just mainly you have an infinity divided by some infinity. Or you have 0 times an infinity. If you have 1 to the infinity power. If you have infinity raised to the 0 power. If you have 0 raised to the 0 power. Or if you have infinity minus infinity. All of those are considered indeterminate forms, and you would have to evaluate these using new techniques. So to reiterate, 0 over 0 is indeterminate form, but if you get 0 over a when you do direct substitution, now a stands for some number, so you get 0 over some number that's not 0, your answer to that limit problem is 0. If you get a number divided by 0, remember, cannot divide by 0, so your answer is does not exist. But if you get 0 divided by 0, that is the indeterminate form. And you are not done. This means that you must do some other work is needed. So this tells you, this is a red flag that you need to go and do some of the other techniques, and these techniques are what we'll be learning in our lesson today. So what's the first technique when direct substitution fails you? It's called the factoring technique. All right, so again, begin and end with direct substitution. So I'm going to look at this limit and I'm going to try direct substitution. So that gives me 3 squared plus 4 times 3 plus 3 over 2 times 3. Oh, negative 3. Why am I doing 3? It should be negative 3. Let me try that again. Negative 3 squared, because I'm doing the limit to negative 3, plus 4 times negative 3 plus 3 over 2 times negative 3 squared plus 5 times negative 3 minus 3. Okay, so let's see. That's 9 minus 12, which gives us negative 3, plus 3, which is 0. And then we got 18 minus 15, which is 3. 3 minus 3 is 0. So notice that we have our indeterminate form here. And because that's the indeterminate form, that's our hint that we need to use this factoring technique. All right, so the factoring technique says, before you can evaluate the limit, so I can't do the limit yet. So here when you do direct substitution, you're evaluating limits. So notice I don't write the limit notation. But when I have to do these other techniques, I'm not going to evaluate the limit yet. So I have to bring down the limit notation. You have to keep bringing down limit notation until you do direct substitution. So it says, okay, what we're going to do now is we're going to factor each of these polynomials. So we're going to factor x squared plus 4x plus 3. And so that factors to x plus 3 and x plus 1. And then we're going to factor 2x squared plus 5x minus 3. That becomes x plus 3 and 2x minus 1. So we factored each of our functions, each of our terms. Now again, I have not evaluated the limit, so that limit as x goes to negative 3, I must write down, bring that down. And then I notice, wait, look, I have a factor of x plus 3 in the numerator and a factor of x plus 3 in the denominator. So that tells me I can cancel that out. So if I simplify this equation, it's now just x plus 1 divided by 2x minus 1. So now that I've factored it out and I was able to cancel a term from the numerator and the denominator, I'm going to try direct substitution again. Maybe that got rid of my 0 over 0. So I'm going to go back to and do direct substitution. Now that I'm doing direct substitution, I am actually evaluating the limit using the properties of limits, just a shortcut to that. So I no longer write my limit notation. So this is where the limit notation disappears. Do not let it disappear ahead of time. And then I'm just going to simplify this down. So it gives me a negative 2 over negative 7, which my answer is positive 2/7. And now I evaluate a limit using our factoring technique. All right, our next method for evaluating limits that give you the indeterminate form is called simplifying complex fraction. Now the hint that you're going to use this technique is if you end up with a compound fraction. And all a compound fraction is you have a fraction, in this case I have 2 fractions, inside of a fraction. So I have a fraction inside of this big fraction problem here. Okay, so that's what tells me that I need to do compound fraction technique. But again, always try direct substitution, because even some compound fractions, direct substitution works, and so you don't want to do any extra work that you don't need to. So I'm going to try direct substitution, and I'm going to plug in 0 in place of my x, and that gives me 1/7 minus 1/7, which is 0 over 0. So yes, I have the indeterminate form. So I got to go back to my limit notation. And now the indeterminate form says, okay, in your big fraction, which term, numerator or denominator, has a fraction in it? In this case, it's our numerator. So we're going to work with that term first. So I'm just going to copy down my denominator like it is. And I'm going to work with the numerator. And then what you're going to do is you're going to try to find a common denominator so you can get one single fraction on top and a single fraction on bottom. And so I notice I have a denominator of x plus 7 and a denominator 7. So my common denominator would be the product of those two terms. So I'm going to make a new denominator for each of these two fractions as 7 times x plus 7. So in this first fraction here, I have changed the numerator by multiplying by the 7. The denominator by multiplying the 7, so that means I need to multiply 1 by 7 as well. So I got to multiply what I did the bottom of the fraction, I got to do the top. And then for my second fraction here of 1 over 7, I've changed my denominator by multiplying by x plus 7. So that tells me I need to take this 1 and multiply by x plus 7. Bring down my limit notation. Bring down my big denominator. Okay, now I have a common denominator. I want to write this over one denominator. And so it's the first numerator minus this denominator. Remember, this is understood to be 1 times all of this, so I got to distribute that negative. This is a common mistake. A lot of students will forget to distribute that negative and write plus 7 here, not negative 7. So be conscious of that you're having to distribute that negative 1. And so now I want to simplify. And I get 7 minus 7, so that's just negative x over 7 times x plus 7. And then denominator is x, which I'm going to choose to write as x over 1, because any number can be written over 1. And so the reason I'm choosing to write it like that is I now have that requirement of this simplifying complex fraction. And the requirement is you have to have a fraction divided by a fraction. So I have a fraction divided by a fraction. And so and we know from previous math classes that in order to simplify fraction divided by fraction, you flip the bottom fraction and you multiply. So I'm going to flip this green fraction over and switch that to multiplication. Now again, I still am just evaluating this function, so that limit notation is coming down. And this limit notation is coming down. And then now that I look at this, I can multiply straight across and I get negative x, 7x times x plus 7. Okay. Then I notice that this x and this x can cancel off because they're products or factors of the term. So I can go ahead and cancel those out. And that leaves me with negative 1 divided by 7 times x plus 7. And now I might have fixed my problem because I canceled an x out from top and bottom. So I might have fixed my 0 to 0 problem. So I'm going to go back to direct substitution. And since at this step I'm doing direct substitution, I don't write that limit notation. That's where the limit notation disappears. And I end up with negative 1 over 49, which is a number. So that works. And I have an answer to my limit problem. That is the technique, a simplifying complex fraction technique. All right, so now we're going to look at our next technique, our fourth technique, which is called multiplying out technique. Okay, we'll use this when you see terms that cannot be factored, but you could kind of break them down maybe. You could try the factoring technique, so this sometimes could work a factoring technique, but not. We're going to try what's called the multiplying out technique. Now, I purposely use this unusual notation on this problem because it might be something that you're not used to. As you can see here, we have our variable as delta x. So we just have delta x. Now, delta x is considered a single variable, just like x is a variable or y is a variable, z is a variable. That's just delta x. Delta x goes together as one variable. And so make sure when you're working this out, you think of that as a single variable. Delta x is very common in calculus as it stands for the change of x. And since calculus is the study of the rate of change, objects in motion as they change in motion, we're going to see delta x quite a bit. And so just kind of get used to that. So I'm going to try direct substitution first. So I get x plus, I'm going to replace delta x with 0 squared minus x squared over 0. That gives me x plus 0 is x, so that's x squared minus x squared, that's 0 over 0. So direct substitution gives me indeterminate form, so I need to try a new technique in order to evaluate this limit. And we're going to try the multiplying out technique. Now the multiplying out technique says we're going to multiply these terms out. So here I have x plus delta x squared. Well, anything squared means it's that term times itself. So I'm going to rewrite that x plus delta x squared as this, and then I still have that minus x squared, and then denominator I still have delta x. And then to evaluate this, I'm going to use the full method. So I'm going to multiply x times x, it gives me x squared, x times delta x, which gives me x times delta x. And I'm just putting that in parentheses so you recognize that's x times delta x. Don't make the mistake of writing x delta x squared, because this delta x is not the same variable as this x. Okay, and then inner terms is x delta x again. And then our outer terms is our delta x variable squared. And we still have this minus x squared over delta x. Let me do some simplifying algebra here. This x squared and this x squared cancels out. I can combine these two terms together to get 2x times delta x plus delta x squared over delta x. Okay, and I notice all terms have delta x in it, so in the numerator I'm going to factor out my greatest common factor of delta x. That leaves me with a 2x plus a delta x over a delta x. And then now I can cancel out that delta x and delta x. So I've canceled out a term with our variable from the top and bottom. So that tells us I might have been able to get rid of our indeterminate problem of 0 over 0. And that leaves us with this 2x plus delta x. So it's time to actually try direct substitution. So my limit notation disappears, and I replace the delta x with 0. And so my answer to this limit problem is 2x. And yes, I can have a variable in my answer. This is the first time you saw a variable in an answer to a limit problem, because the limit was evaluated to the variable of delta x. And this problem originally had two variables, x and delta x. And so our final answer doesn't have any delta x in it, because we evaluate the limit as delta x approached a number, which was 0, but it can have the other variable left over. So that would be our answer to that problem. Our last technique that we're going to learn today is called the rationalizing technique. The hint where you might need to use this is if you see a radical. Here is a square root, could be a cube root, a fourth root, but you see a radical in the problem. That's usually a hint that you might want to use this technique. But again, begin and end with direct substitution. So I'm going to try substituting in place of every x 1 and seeing what I get. 1 minus 1 is 0. 4 minus 1, 1 squared is 1. 5 minus 1 is 4. Square root of 4 is 2. 2 minus 2 is 0. So yes, I have the indeterminate form. So I got to go back to my limit notation. And we're going to use the rationalizing technique. So the rationalizing technique says, okay, first you got to identify where your rational term is. And if it's a binomial, which we have two terms here, I guess I should highlight that as two terms so you can see it. So we have the first term, which is the radical, and then we have our second term, which is the number 2. And so we have a binomial. So if it's a binomial, you're going to multiply by its conjugate. If it's just a single radical, like square root of x minus 2, you'd multiply by itself, square root of x minus 2. But here, because we have two terms, a radical term and a constant term, we're going to multiply by its conjugate. And so what that does is it tells us we take our original fraction, so here's our original function, and then we're going to multiply this entire function by the conjugate of the radical term, which all the conjugate means is this sign between the terms, this sign here, and you do the opposite. So you change the sign there. And then whatever you do to the top of a fraction, you have to do to the bottom. And whatever you do to the bottom, you have to do the top. So we're going to multiply by that. So I'm multiplying by 1. I'm just choosing to write my 1 in this very unique method. So it works out. All right, now here's another time saver for you. And you'll always want time savers in calculus if you can. The original problem had the radical in the denominator of the fraction. So that's where my problem child is in my indeterminate form. So I'm going to work with the denominator. So this numerator, I'm just going to keep it as products. I'm not going to multiply it out yet. Sometimes you might have to, but usually you don't. And you want to keep that because the whole point is we need to cancel something from the top and the bottom. In order to cancel something out, it needs to be in factored form. And so the top right there, what I just wrote on top, that's factored form. So I'm going to keep it in that factored form. So this bottom here, I have to multiply out using my full method. So my first terms is square root term times the square root terms. That just becomes a square root term quantity squared. So the square root cancels out with the square, and it just leaves us with that term. And then my outer terms just becomes positive 2 times the radical. My inner term is negative 2 times the radical. So 2 times radical minus 2 times radical, they cancel out. And that will always happen. That's by design. So you notice my radicals canceling out in the bottom. And then I take my last terms, negative 2 times 2, which gives me negative 4. And so that's how that simplifies down. All right, let's do a little bit more simplifying of that bottom term. And I end up with 1 minus x squared. Well, 1 minus x squared, I need to be able to recognize that as the difference of squares. And so I'm going to factor that, because remember, we need to try to factor this as much as possible so I can cancel something out. And 1 minus x squared factors as 1 minus x times 1 plus x. And now I have everything factored. I can cancel out these common factors. And I have the limit as x goes to 1 of the square root of 5 minus x squared plus 2 over 1 plus x. Okay, so that's how that factored down to. And looking at that, I've canceled something involving our variable x from the top and the bottom. So hopefully now that solved my indeterminate form problem. So I'm going to go back to direct substitution, replace every x with 1, and see what I get. So this is 1 squared is 1, 5 minus 1 is 4, square root of 4 is 2, 2 plus 2 is 4, over 2, which is 2. So my answer to this problem is 2. And that is our rationalizing technique. So these are the techniques that you need to be able to solve. Remember, begin and end with direct substitution. That is your default method. You always try that first. If you get the indeterminate form, then you need to go back and try one of these techniques we talked about in this video, which is our factoring technique, where you factor everything and see if something cancels out. Simplifying the complex fraction so that you find common denominators of the compound fraction, and so that you can get a fraction over fraction and then cancel something out from top and bottom. Multiplying out technique, where you multiply things out and then factor again and see if something cancels from the top and bottom. And finally, the rationalizing technique, where if you have a radical, you multiply the top and bottom by the conjugate of that radical, multiply out, factor again, and see if anything will cancel out from top and bottom. Those are your techniques that we will use in part 1 of solving limits algebraically.